Welcome back, and one more the problem we are going to solve on free longitudinal vibration. So the problem here, to find the natural frequency of the system which is shown in the figure, right? And this is the figure we have taken. So this is the mass, is the 10-ton load is going to, 100-ton load is going to be acting in the system, and the springs K1, K2 and K1, next one K3, K4, K3, K6, K6, K5, and these are going to be the different springs they are going to be arranging. That means the total load, whatever it is coming, it's absorbed by the springs and giving to the foundation. So in this case, we need to find out the natural frequency for this longitudinal vibration. So can you see here, the K1 is equal to K2 is equal to K3, and similarly that is equal to 1000 Newton meters. All the springs have the same stiffness of this one, that is going to be 1000 Newton meter. So then how could you solve it here? There we can see here K1, K2, K3, they are in the parallel to each other. Then we need to write the one equivalent spring stiffness constant. And here K3, K4 and K3 is another spring constant, equivalent spring constant we need to write. K6, K5, K6 and K5, another equivalent spring constant. I am going to simplify this diagram in this way. So this is going to be the mass. This is the equivalent spring stiffness, and here also another stiffness. This is going to be, I am going to say K equivalent 1 and 2. This is going to be the three springs, equivalent stiffness is going to be KE 1, 2. And similarly, this is going to be KE 3, 4. And for this one, K 5, 6 equivalent stiff constant, I am going to be stiffness constant, right? And now it is in the series condition. Now we need to simplify this one into a single mass and single spring. K equivalent, I am going to be say that K equivalent is equal to KE1 to KE3, 4, KE5, 6, and I am going to be writing that equation 1 by KE is equal to 1 by KE 1, 2 plus 1 by KE 3, 4 plus 1 by KE 5, 6, right? And then what is the KE1, 2 value? K1, K2 and K1. So then K1, K2 values are going to be 1000 Newton per meter square, and this is equal to 3000 Newton per meter, and this is also 3000 Newton per meter, right? And what about this one? This is also 3000 Newton per meter. Once we are getting these equivalent stiffness values, then we can substitute in this equation. So in this equation, then finally, what is the KE value we are going to be getting? Then once you are substituting 1 by 3000, 1 by 3000, 1 by 3000, that finally I am getting 1000 Newton meter. So this is the equivalent stiffness constant of these springs. So once you calculated the equivalent stiff constant, then we need to find out the natural circular frequency, that's going to be omega n. We are going to be calculating, that is going to be square root of Ke by m, right? So Ke is equal to 1000 Newton meter and the mass is equal to 100 ton newtons we are going to be taking. Then finally, once you are going to be substituting this equation, omega n is equal to, what is the how much value we are getting? That's going to be 0.99 radians per second. So once you are calculating the natural circular frequency, then we can calculate the natural frequency, that is equal to Fn is equal to 1 by 2 pi into omega n, right? So from this one, what we are getting, 0.99 by 2 pi. Fn is equal to how much value we are going to be? That is 0.157 H. So this is the natural frequency of this system when the load is acted, 100-ton load is going to be acting on this system. Then we are going to be calculating the natural frequency of the system. Thank you.